We will now discuss the different techniques of integration. The different techniques of integration are necessary for us to evaluate some integrals that cannot be evaluated by using any of the fundamental integration formulas. An example is the integral of e raised to 5x times cosine of 3x dx. This one can be evaluated using a technique called integration by parts. Another integral is, say, x all over the square root of x minus 4 dx. This one can be evaluated using algebraic substitution. The integral of dx or x squared dx over the square root of x squared plus 4 can be evaluated using trigonometric substitution. Another is, say, the integral of 2x minus 7 quantity dx all over x minus 3 squared x squared plus 1. This one can be evaluated through integration by partial fraction. Another is the integral of, say, dx over 1 plus sine x plus cosine x. And this falls under integrals involving sine and cosine or rational functions. Rational functions of sine and cosine. And so these are the different topics that we will discuss about the different techniques of integration. So we start with the first technique, which is called integration by parts. Alright, we recall from differential calculus the differential of the product uv, which is equal to u dv plus v du. We solve for u dv, so that will be equal to the differential of uv minus v du. We then integrate both sides. We integrate all terms. So the integral of u dv is equal to, we know that the integral and the differential are inverse operations. So the integral of the differential of ub is u times v minus the integral of v du. This will be our working formula for integration by parts. So for a given integral u dv, we will select our u and our dv. We need the product ub. Now the function v can be determined from the differential of v by evaluating the integral of dv, and then subtract the integral of v du. Again, v is obtained by integrating dv, and du can be obtained by differentiating u. So if we are to apply integration by parts for a particular integral, we have to select our u and our dv so that the resulting integral v du is simpler compared to the original integral u dv. Alright, so we can have a better understanding of this through several examples. So let's start with the integral of x e to the negative 3x dx. So for the given integrand, we have to select our u and our dv. Our selection for u is between x and e to the negative 3x. So let us say that our u is equal to x and our db is e to the negative 3x dx. The differential dx is always part of db. No? Dx is always a part of db. So in our formula, we need to find first our v as well as the differential du. So if u is x, taking the differential of u is du and the differential of x is of course dx. In here, dv is equal to negative e to the negative 3x dx. So if we are to integrate, of course it will give us v, and the integral of e to the negative 3x dx is negative 1/3 e to the negative 3x. Alright? So we now apply the formula u times b. We just have to multiply u and b. That will be x times negative 1/3 e to the negative 3x. Then minus b du. So b du. And that will be negative integral of negative 1/3 e to the negative 3x. That is our b. And then du is dx. Continuing, x times negative 1/3 e to the negative 3x is negative 1/3 x e to the minus 3x. Then negative times negative 1/3 is positive 1/3 integral of e to the negative 3x dx. So there's still one integral to evaluate. No? Negative 1/3 x e to the minus 3x plus 1/3, and the integral of e to the negative 3x dx is negative 1/3 e to the negative 3x plus c. Let us polish our answer. Negative 1/3 x e to the minus 3x. 1/3 and negative 1/3 is negative 1/9 e to the negative 3x plus c. We finalize our answer by factoring negative 1/9 e to the negative 3x times, so negative 9 divided by negative 3 is positive 3x. Okay, and then this one is positive. We have factored negative 1/9 e to the negative 3x, so that will be 1 plus c. So that is our answer. (701) The integral of x squared cosine of x. So let us choose our u. Of course, there's a dx there. We choose our u. That will be equal to x squared, and then db is cosine x dx. Alright? Our du, we take the differential of x squared, which is 2x dx, and then we integrate cosine x dx, which is sine of x. Of course, there is a constant, but we will just reserve that constant in our final answer. So, the answer should be ub minus the integral of b du. Our u is x squared, and b is sine of x. Then minus the integral of v is sine x, and then du is 2x dx. Let us write that as negative 2 integral of x sine x dx. So I'm just rearranging the terms in the integral. No? Now, notice the appearance of x in the integral together with sine x. So for this one, we will apply a new integration by parts. No? Our u is now x, before it's x squared, then db is sine of x dx. So we are applying integration by parts twice for this particular integral. No? So if u is x, then du is dx, and dv is sine x. So integrating sine x dx will give us negative cosine of x. So x squared sine of x minus 2 quantity. Once again, the answer for integration by parts is u times v. So u is x and v is negative cosine x minus the integral of v du, which is negative cosine of x dx. So x squared sine x minus 2 times x times negative cosine x becomes positive 2x cosine of x. And then negative 2 times negative is negative 2. Again, negative 2 multiplied to negative times negative is negative 2. And the integral of cosine x is sine of x plus c. So, this is one particular example where we use integration by parts twice. In the first time that we use integration by parts, what will happen if we chose cosine x as our u? And our db is x squared dx. So if we are to take the differential of cosine x, that will be negative sine x dx. And if we integrate x squared dx, it becomes x cubed over 3. So ub will be 1/3 x cubed cosine x minus the integral of v du, which will be negative 1/3 or positive 1/3 x cubed sine x dx. And at this point, you should have realized that the resulting integral is more complicated than the original one. The original integrand is x squared cosine x dx. By applying u equal to cosine x and dv equal to x squared dx, you will be getting an integral which is more complicated than the original one. So, that only shows that we have chosen the incorrect set for u and db. So once realized, no, the only thing we have to do is to use the other function x squared as our u. No? So this is the wrong selection for u and db. Let us evaluate the integral of y, square root of y plus 2 dy. Before we select our u and our db, let me rewrite this as y times y plus 2 raised to 1/2 dy. Alright? Then, we select our u. Let us use y as our u. And our dv is y plus 2 raised to 1/2 dy. So du is dy, and integrating y plus 2 to the 1/2 dy, applying the power formula will give us y plus 2 to the 3/2. No? 1/2 plus 1 is 3/2, all over 3/2. So, for our answer, it will be u times b, so y times 2/3 y plus 2 to the 3/2 minus the integral of 2/3 y plus 2 raised to 3/2 du, which is dy. So it will be 2/3 y times y plus 2 to the 3 halves minus 2/3. For y plus 2 to the 3 halves dy, you will apply once again the power formula, where u is y plus 2 and n is 3 halves. So y plus 2 to the 3 halves plus 1 is 5 halves all over 5 halves plus c. So 2/3 y plus 2 to the 3 halves minus 2 times 2 is 4, 3 times 5 is 15. So 4 over 15, y plus 2 raised to 5 halves plus c. Let us refine our final answer by factoring 2 all over 15. 2 over 15, y plus 2 to the 3 halves. Okay, so we factored 2 and 15 divided by 3 is 5. We have factored y plus 2 to the 3 halves, so there remains y. And then minus, we have factored 2 from 4, so that will be 2. And then we took away 3 halves from 5 halves, no? Because we have factored y plus 2 to the 3 halves. So you'll be getting y plus 2, 5 halves minus 3 halves is 2 halves or 1 plus c. So 2 over 15, y plus 2 to the 3 halves, 5y minus 2y is 3y, negative 2 times 2 is negative 4 plus c. Okay? Example number 4, e to the x sine of 2x dx. Okay? So, what do you think is the appropriate u here? Let me use e to the x, and my dv is sine 2x dx. So my du, the differential of e to the x is e to the x dx, and then the integral of sine 2x dx is negative 1/2 cosine of 2x. Derivative of 2x is 2, so 1/2, and the integral of sine is negative cosine. So u times b is e to the x times negative 1/2 cosine 2x is equivalent to negative 1/2 e to the x cosine 2x minus the integral of b du. So negative 1/2 e to the x cosine 2x dx. Alright? Or negative 1/2 e to the x cosine 2x plus 1/2 integral of e to the x cosine 2x dx. So we have the integral e to the x cosine 2x dx, which is quite similar to the original integral e to the x sine 2x dx. No? Sine 2x in the original integrand becomes cosine 2x in the resulting integral. So if we are going to apply once again integration by parts to this integral, cosine will return back to sine. So let us see what will happen. Our u is e to the x, and dv now is cosine 2x dx. du is e to the x, and b is the integral of cosine 2x dx, which is 1/2 of sine 2x. So negative 1/2 e to the x cosine 2x plus 1/2 quantity ub, that will be 1/2 e to the x sine 2x minus the integral of 1/2 e to the x. There is there should be a dx here. So 1/2 e to the x sine 2x dx. So notice the recurrence of the original integrand. E to the x sine 2x. So let me rewrite this as negative 1/2 e to the x cosine 2x plus 1/4 e to the x sine 2x minus 1/4, okay, of the integral of e to the x sine 2x dx. So as mentioned earlier, the solution returns back to the expression e to the x sine 2x dx. What we will do at this point is we will transpose. If we are going to apply a new integration by parts here, sine becomes cosine, and then iterating that, cosine becomes sine, and it will be a never-ending process. All right. So what we are going to do is we will transpose this entire term of negative 1/4 integral of e to the x sine 2x to the left side. And what do we get? It becomes positive 1/4 integral of e to the x sine 2x dx plus, of course, the original integral e to the x sine 2x dx equal to negative 1/2 e to the x cosine 2x plus 1/4 e to the x sine 2x. And we combine these two, that will be 1/4 plus 1 or 5/4. Alright, so that will be 5/4 of the integral of e to the x sine 2x dx equal to, let me simplify this, 1/4 e to the x times, let me start with this one, sine 2x minus 4 divided by 2 is 2 cosine 2x. Alright, and how do we get rid of the coefficient 5/4? By multiplying both sides by 4 over 5. Actually, we can cancel 1/4. We can cancel 1/4. So, finally, we have e to the x sine 2x dx equal to 1/5 e to the x times sine of 2x minus 2 cosine 2x plus c. Okay? So, if you are given an integral, and by the application of integration by parts, there is a recurrence of the original integral, what you will do is you transpose that integral to the left side to combine with the original integral, and then you just add up the coefficients to find the final answer. So we're now down to example 5, the integral of ln x dx. We have the integral dx over x that leads to the natural logarithmic function. The integral of dx over x is ln x, but we do not have, as of the moment, the integral of ln x. And to find the integral of ln x is to apply integration by parts. So my u is ln of x. Remember, you cannot separate ln and x. No, it's one function. It is one function that you cannot separate ln from x. So your u is ln of x, and your dv, of course, is dx. So take the differential of ln x is 1 over x dx, and the integral of dx is x. So u times b, just multiply u and b, that will be x ln of x. Then minus, you multiply these two, integral of x 1 over x dx. But of course, we can cancel the x here. So x ln x minus the integral of dx is x plus c. Right? So you can factor x ln x minus 1 plus c. Okay? How about the integral of arctangent of x dx? We have an integral dx over 1 plus x squared that results to the arctangent function. Okay? But we do not have the integral of arctangent. So to find the integral of arctangent is to apply integration by parts. So our u is arctan of x, db is dx. Then du, what is the derivative of arctangent x? 1 over 1 plus x squared dx. And then b is the integral of dx, which is x. So u times b, that gives us x, arctan of x. Then b du. So minus the integral of x over 1 plus x squared dx. So x arctangent of x minus, to evaluate this integral, x dx over 1 plus x squared, we take on 1 plus x squared as our u, and du will be 2x dx. So 2x dx is our du, then times 1/2. So negative 1/2, and du over a squared, no, du over u. No? 1 plus x squared is your u. So du over u gives us ln of 1 plus x squared plus c. Or x arctangent of x minus 1/2 becomes the exponent. No? One of the properties of ln. So the coefficient becomes the exponent. So that will be ln of 1 plus x squared to the 1/2, or equivalent to the radical square root of 1 plus x squared plus c. So I think this is example 6. No? That's right. This is number 5. Number 6 is arctangent. Okay. So one last example. The integral of secant cube theta d theta. What we have here is a power of secant, and the exponent is positive odd. Remember, when we were discussing about powers of secant, we considered only exponents that are positive even integers. No? For exponents of secant or cosecant, which are positive odd integers, we will apply integration by parts. Alright? So our u will be secant theta. So we're going to split secant cube into secant theta and secant squared theta. Secant squared theta together with d theta. Why are we doing that? Because we know the exact integral of secant squared theta d theta. Or secant squared theta d theta is the exact differential of tangent theta. Alright? So we take the differential of secant, which is secant tangent. And then the integral of secant squared theta d theta is tangent theta. Or u times b gives us secant theta tangent theta minus the integral of b du, which is tangent theta. Okay, sorry. Tangent theta times secant theta tangent theta d theta, or secant theta tangent theta minus secant theta tangent squared theta d theta. So the degree here is still 3, no? Secant raised to 1 tangent squared, so the degree actually is 3. The original integral is also of degree 3. So what do we do next? Let us apply an identity to tangent squared theta. Tangent squared theta is secant squared theta minus 1. It comes from the identity 1 plus tangent squared equal to secant squared, right? So tangent squared can be written as secant squared minus 1. So we have secant theta tangent theta minus the integral of secant times secant squared is secant cubed theta d theta. Then negative times negative 1, that will be positive integral of secant theta d theta. See that? Tangent squared theta becomes secant squared theta minus 1. And then we are splitting this into two integrals, secant cube minus secant. Secant cube minus secant. And it is preceded by a negative sign. So negative secant cube and positive secant. Okay? What do we see here? We see that secant cube theta d theta recurs in the solution. So we know how to deal with this. We can transpose this to the other side. So negative 1 to the other side becomes positive 1. So this is now equivalent to 2. Integral of secant cube theta d theta. So see that there is a coefficient 1 here, and it adds up to another coefficient 1. That is why it becomes 2. Okay? So we have here secant theta tangent theta plus the integral of secant theta d theta is ln of the absolute value of secant theta plus tangent theta. Okay, then let us reserve the constant later. So we now divide everything by 2. That will be secant cube theta d theta equal to 1/2 of secant theta tangent theta plus ln absolute value of secant theta plus tangent theta plus c. Or we can distribute 1/2 secant theta tangent theta plus 1/2 ln, and we know that that coefficient 1/2 becomes the exponent, so we can write this as ln of the square root of secant theta plus tangent theta plus c. Okay, so try to remember that the integral of secant cube theta d theta is 1/2 secant theta tangent theta plus ln of the square root of secant theta plus tangent theta, because we will be encountering this integral in the future. Okay, so you now work on the following integrals. Let's have some exercises. You evaluate x squared e to the x over 2 dx, e to the e to the 2x cosine 3x dx, t all over the cube root of 2 minus t dt, the integral of x ln of x dx, the integral of, let me see, x arcsine of x dx. Okay, after this we will discuss the solution.